Hello and welcome to this video on ideal gases. Today we're going to talk about what's an ideal gas versus a real gas, and we're going to work with this ideal gas equation. So grab your notebook and something to write with and let's get started. So the first thing that we want to know is really just what's the difference between what we call a real gas and an ideal gas. And we make the assumption that most gases actually behave ideally, but there are some circumstances where they're going to deviate from that. We don't need to do any calculations with this. That's for a much further advanced chemistry, but we do want to know what the general differences are between them. And so what we see is that with real gases, they are going to have high pressure, and so these are pressurized gases, or they're things that maybe have been compressed. They have low temperatures. They are going to have really a little bit slower molecular motion overall for a gas. So they're very fast still when we're considering solid liquids and gases, but relative to an ideal gas, they're going to be quite a bit slower. And that's going to reduce the space between gas molecules. So we're really kind of squeezing these gas particles together. And when we do that, what we see is that they are going to have intermolecular forces that start to impact them. So our collisions are no longer going to be completely elastic. There's going to be some interactions between them, and that starts to change their behaviors from what we normally associate with gases. The opposite is the case with ideal gases, and this is why we assume ideal gases. It makes our life a little bit easier. And so now we're going to talk about low pressure, high temperature, very fast molecular motion, and then having quite a large amount of space between each one of those gas molecules. And so when that happens, they're not going to be encountering each other very often, and so we really figure that there's no intermolecular forces. And for our purposes, we really apply this ideal behavior to all of our gases. So even though they can behave a little bit differently, most gases at 298 Kelvin and 1 atmosphere tend to behave like an ideal gas, and that's what we run into in our world, okay, because 298 Kelvin is actually 25 degrees Celsius, which is what we consider to be room temperature. So that's what we actually normally look for. So this is the ideal gas equation. You're going to want to have this written down somewhere. And we now can find the number of moles of gas. And so what we know is that the number of moles of gas actually impact things. And so that's what we see here with the N. And then we also have R, and R is going to be a gas constant. Now, it's dependent upon what our pressure unit of measure is going to be. And so there's a couple different things that we see here. R can be two different values, and it's always a constant, so it'll be one or the other for us. So R can be 0.0821, and that's when we have a pressure of atmospheres. And so this is going to be for the unit. Now people get confused when I do this. Please know that this next thing I'm going to write down is actually the unit of measure. It's liters times atmospheres divided by moles times Kelvin. So this here is our unit of measure, okay? And you don't want to confuse that with anything else. This is not an equation. This is a unit of measure. So this is when we have pressure in atmosphere. Okay. Now, if pressure is in kilopascals, which oftentimes it may be as well, is in kPa, we are going to see that the R value is going to be 8.31 liters times kilopascals divided by moles times Kelvin. So we're still in Kelvin, that hasn't changed, but because of the fact that we have different units of pressure, and really that whole conversion of 101.3 kilopascals for every 1 atmosphere is why we have the difference. You can actually multiply this by 101.3 or divide this one by 101.3, and you'll find that you'll get the other one, or pretty darn close to it. So that's where those come from. What we want to be able to do is apply these in order to be able to solve some problems. And we can actually solve for pressure, volume, moles, or temperature, knowing that R is always a constant. We always know that it's going to be one of these two numbers. We just have to determine what our pressure value would be. Okay? If you don't have pressure and you're given pressure, you would just use one of those to find pressure. So let's take a look at a couple of example problems. We're going to do one that uses we'll do one that uses one constant and one that uses the other constant. So here we have how many moles, so we want to know moles, okay, of gas are in a 3.2 liter sample of gas at 25 degrees Celsius and 156 kilopascals. So remember, we have to have this in Kelvin. So 25 plus 273 gives us our 298 Kelvin. So we'll just go ahead and do that and know that we're going to apply that. So now what I'm going to do, I'm using the PV equals nRT. Okay, PV equals N for moles, R for gas constant, and T for temperature. We want to know how many moles. I'm actually going to algebraically solve for this just straight up. So if I want to know that, I'm going to divide both sides by RT, which means that N is going to equal PV divided by RT. Now, if you want to plug in your numbers and then solve for your unknown variable, you're welcome to do that. I usually set mine up this way. Either way is perfectly fine, okay? So what I want to do is I want to pull my p-value. My p-value was right here, so that's 156 kilopascals. Okay. I'm going to multiply that times my liters, my volume, which is 3.20 liters. And then I want to divide that by my temperature. So I'm going to put my temperature here, which is 298 Kelvin. And now I have to figure out which one of my constants do I need to use. Since this is in kilopascals, we want to use the 8.31 liters times kilopascals divided by mole times Kelvin. Okay, so that is our unit. Once we have that, we can cancel out those units. So I'm going to grab a different color here. I see kilopascals on the bottom and on the top, so those cancel. I see liters on the bottom and on the top, so they cancel. This is actually Kelvin on the top and this one's on the bottom, so these two cancel and I am left with moles, which is the unit I wanted to find out. So now if I go ahead and I calculate those out, I find that I get 0.2015 and some other numbers. So with proper sig figs, okay, we have 3.20. There's 3 sig figs there, here, and here. So 3 sig figs is what we want at the end. And so that's going to give me 0.202 moles of gas. And so that would be our correct answer. Okay, so again, we had to use this for our R value because we were in kilopascals. So that is our R value that we used. So let's try one more, but now using the other R value, the other gas constant. And so our other gas constant is going to be for atmospheres. So in this problem, we're going to see that it says how many moles of gas are in a 15-liter sample of gas at 25 degrees Celsius. Remember, that's 298 Kelvin, okay, and 3.81 atmospheres. Again, I'm solving for moles. So we're going to set this up. Our PV equals nRT, so N is going to equal P times V divided by R times T. Okay, so you could be solving for volume or something different, so just keep that in mind. We're just solving for this in our example, but you could solve for any of them. So now what we want to do is add in our values. So I have 3.81 atmospheres times 15 liters, so it's in a 15-liter chamber. And now, because this is in atmospheres, we want our other gas constant value. So that one is 0.0821 liters times atmospheres divided by moles times Kelvin. Okay, remember, this is just our unit of measure, so nothing else is going on there. And then 298 Kelvin. Let's again look at how we canceled out those units to double check that we have things in the right place. So atmospheres here and below, on top and bottom, they cancel. Liters on bottom and top, they cancel. And Kelvin on top and bottom, they cancel. And we're left with moles, which is what we wanted to know. So when I do this calculation, we ended up getting, let's see, I did that earlier, 2.3359. Okay, again, we had 3 sig figs, and oh, this one only has 2 sig figs. So my final answer has to be to 2 sig figs, which means this is going to be with sig figs, okay, with our significant figures, this has to be 2.3 moles of gas that we have. So those are a couple examples. Remember that you could solve for any of these values with the exception of R, it's our constant, and we will do some more practice when we get back to class.